Recording in progress.
So tell me, when should I start? I will.
Okay, on my clock it's 1 p.m. right now. So welcome back everyone from the coffee break. For me it was lunch. I don't know where you are. And now for our first speaker we have LPHYS'23. If you like, I can let you know 5 minutes before our time's up. Is that okay?
Okay, great.
Perfect.
Thank you.
Thank you.
Okay, so I'm going to tell you about quantum-enhanced multi-parameter estimation and compressed sensing of a field. And this work has been done together with Youssef Bamara, who is a PhD student, and Manuel Gessner, who is now in the University of Valencia. So first, I will introduce shortly the field of spin squeezing. It is a central point of my talk. And then what I call a squeezed Mott state, where the atoms are squeezed and in an optical lattice in the Mott configuration. And I would like to tell you how this kind of system can be used to perform the estimation of many parameters, multi-parameter estimation with some quantum gain coming from the quantum correlations among the atoms. And also how one can perform quantum sensing using this system. So first of all, let us consider single parameter estimation. Many very sensitive atomic sensors are based on the precession of a spin 1/2. And for example, this is the case of atomic clocks. In the case of an atomic clock, one takes an ensemble of n atoms, prepares all the atoms pointing the same direction. So for example, here, the atoms are represented, the spin of the atoms is represented in the Bloch sphere, and all the spin 1/2 point the x direction. And when one looks at the precession of this big spin of length n/2 around the Bloch sphere at the frequency which is given by the energy difference between the two levels. And this is the way one measures the frequency in an atomic clock. But the quantum nature of the spin components makes it that there is some quantum uncertainty in the position of this big spin. In particular, one prepares all the atoms in an eigenstate of the component x of the collective spin, sum of all the spin 1/2 here. And the fact that the three components x, y, and z of the spin do not commute makes it that there are some fluctuations in the other two directions, that is y and z. And in particular, the uncertainty, the fluctuations in the direction y makes an angular uncertainty on the position of the spin. And so if you want to measure precisely the angle, the accumulated angle, this gives you an uncertainty. When the atoms are independent, the fluctuations in the component y and z are the same, and they are given by the Heisenberg uncertainty principle. That is, the products of the square root of the variances in y and z is n/4. And so this gives some angular uncertainty, which is this width, that is square root n, divided by the length, which is n, that is 1 / square root n, which is also called projection noise in atomic clocks, and it has already been seen. One can, however, reduce this angular uncertainty by creating some correlations among the atoms. And this is precisely spin squeezing. That is, one can make the fluctuation smaller in the direction y, giving the angular direction of the spin, and then increase them in the other direction. And one introduces to quantify this reduction a parameter, which is this psi, which is the spin squeezing parameter, which is directly related in the precision that one can get in measuring this precession frequency. So in this business, the parameter that we want to measure using the atoms is the phase of precession. And here is a single parameter. It is all the atoms measure the same one. before going to multi-parameter estimation, I would like to say, how can one achieve spin squeezing? There are many ways, possible ways. But one possible way is to use atomic interaction in a Bose-Einstein condensate with two internal states, so that I have a spin 1/2 attached to each atom. The atomic interaction actually create a nonlinear part of the Hamiltonian that is proportional to Sz square. Sz is this Z component of the collective spin. Sz is the difference of the number of atoms in internal state A and B. And you can see that this kind of Hamiltonian will make the squeezing, because you can read this Sz square as an Sz times Sz, and so you can interpret this as a usual Hamiltonian with a Larmor frequency which depends on Sz itself, meaning that if initially your atoms are independent, so your noise circle is like this, then if Sz is positive here, the precession will be on the right, if it is negative, on the left, and this noise circle becomes an ellipse. It squeezes. And then by a single atom operation, you can put it vertical, and you have this spin squeeze state that is very much suited to measure the angular precession. And why do we have this Sz square? It's easy to see. If initially we prepare our condensate in a superposition of two internal states, that is the internal state A and B, all the atoms are in a state A plus B over square root of 2. We can expand this state over the Fock states, that are states with an exact number of atoms in A and B, and we see that we have some probability distribution in A and B. And if we now write the energy, for example, we imagine that the two components A and B do not interact, the energy is the sum of the two, and we write the energy of the atoms in internal state A, we expand it around the mean atom number Na, which is n over 2, total n over 2. We have several terms. We see that we can do a Taylor expansion. At the first term, we have chemical potential appearing, that is the derivative of the energy with respect to Na. And the second derivative is there, the mu over dn times Na minus the average, that is n over 2 square. But this term here, Na minus n over 2, is just Sz. So here I get the Sz square term, this squeezing term. And I can see immediately that the coefficient in front will be proportional to the S-wave scattering length, characterizing the interaction between the atoms. Okay, so this was realized indeed in Bose-Einstein condensate, spin squeezing, and it was also shown that it can improve the measurement of a single parameter. Now we want to go further, and actually we propose to generate in this way a spin squeeze state, but at the same time we want to split it and freeze it in an optical lattice. That is, we imagine that initially we prepare our condensate in a very shallow lattice, and we put all the atoms in a superposition of the two internal states, A and B, so that the squeezing dynamics starts. But at the same time, we ramp adiabatically the lattice. And at some point, we cross the Mott transition. That is, we end up with one atom per site, so there is not any more squeezing dynamics, but the correlations among the internal states of the atoms are preserved. And so I end up with what we call a squeezed Mott state. There is no condensate anymore. We broke up the condensate, but we kept the correlation which were built up when the system was in the superfluid phase, when every atom was speaking to every atom. And I added one slide, a theoretical slide, if you are interested to understand how one can describe this. the idea of the adiabatic evolution is that you take your initial state, expand it over the Fock states, and then when you wrap the lattice, each of these Fock states will evolve with some phase, which is represented here, which depends on how many atoms in A and in B are there and the lattice height. And this phase builds up the squeeze state. And we were showing in some previous papers that one can, in this way, create a squeezed Mott state with many atoms in 3D. And we were also showing with few atoms with the exact simulation that one can store in this way even more than squeezed states, like very quantum states, like Greenhorn-Zeilinger states. Okay, so now imagine that we have this to our disposal. We have in an optical lattice, 1 atom per side. All these atoms, they are 2-level atoms, but they share correlations. They are squeezed as an ensemble. And the idea is that we would like to use this system to perform multi-parameter estimation. That is, now I imagine that I don't want only to measure one phase like in the atomic clock, but many phases. And these phases are proportional to some local field. For example, imagine there is a magnetic field along the direction Z, for example. I know the direction, but the amplitude is random. I don't know it at all. So I prepare all my single atoms pointing the direction X, and then they will precess locally according to the local field. And so what the parameters I want to estimate is these phases of precession, which give me information about the local field. I want to map the field in this way. So if I use independent atom, the initial state it's written here, will be just each atom, each spin 1/2 prepared along X, and then I will have to measure locally the phase. The imprinting of the phase proportionally to this magnetic field, let's say, is represented mathematically by a unitary operator like this, where locally I act with the operator SZ to turn the spin 1/2 the position I. But now I want to take into advantage the fact that I have a correlation shared among all this ensemble of atoms. And so I don't want to measure locally the phases separately. I want to perform collective measurements, because my initial state will not be independent atoms like this, but it will be this squeezed Mott state, which I can represent such that all the atoms are initially pointing X, but then I act with this SZ² Hamiltonian, which I wrote here. Simply, the capital SZ is the sum of the small SZI. Okay, so I want to perform collective measurement to use the correlation. What I could do is, for example, like in an atomic clock, I can measure the collective spin, the sum of all the spin. If I measure capital SY, this is a component of the collective spin, the sum of all the small spins along Y, one can show that I can get an information about the sum of all these phases. That is the average phase. And I can get it with some quantum gain if my initial state is squeezed. So this is just the same thing as for the clocks. It is very nice. But actually, I want to access to all the parameters at each point. And so if I have n of them, I need n independent linear combinations of the parameter. And here I have just one, the one which is 1 plus 2 plus 3 plus 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 plus. I want also all the other combinations. And we found a simple way, that is by performing, if we are able to perform spin flips and spin rotations locally, we can change a sign of the combination. That is before here, it's written in this line. In the middle, there is the the moment in which we imprint the phase on a certain site. By performing 2 rotations before and after the phase imprinting, we can change the sign in front of that particular parameter. And so we can access different combinations. And so what are the combinations that we have to measure? Actually, the combinations that we have to measure are, for example, those corresponding to the Hadamard transformation. That is, are n independent linear combinations where the coefficients of the combination are just +1 or -1. So starting from our initial signal that I put in a vector, this theta k, one can act with this matrix H, which is made of +1 and -1. I can tell you in a minute how it is built. And I can obtain the combinations, and I can also do, of course, the inverse operation. So this Hadamard matrix here, defined for powers of 2, is constructed in a recursive way. You start with 1, and then for n equal 2, if you only have 2 sides, you put the same 1, 1, 1, 1, -1. And so in this case, the 2 combinations, which are the 2 lines of the matrix, is the sum of the 2 parameters and the difference of the 2 parameters. But then you can extend it for larger and larger numbers. Each time you take the previous matrix, you copy it, same, minus the same. Okay, so here already I can show you some results. So we take a signal. In this case, it is a 2D signal, scalar signal. That is, we encode in the gray. You consider the first image is our signal. The gray means the value of the parameter that we want to imprint in the atoms. And so there is, it's 512, 512. So imagine that I have 512 square atoms in a lattice. And I imprint in each of them some phase which is proportional to the signal at that point. So I imprint on the atoms, and then I read it. And there are 2 different cases. So the central figure here is when the atoms are prepared in a coherent state, that is, they are independent. Still, so I have some noise. This noise is the quantum noise. I repeat the measurements 10 times. That is, I have to measure each of the Hadamard coefficients. Here they are 512 square. I measure them, each of them, 10 times. And then I reconstruct the image by inverse Hadamard transformation. For the same number of measurements, in the center, you see the result when you use an ensemble of independent atoms. And on the left, you see the results when you use an ensemble of spin-squeezed atoms by this SZ² squeezing mechanism. And one can calculate easily the gain, that is the quantum gain that one gets if we use a spin-squeezed state with respect to using independent atoms. I can measure these parameters, that is the value of my 2D field, with a precision which is increased by this quantity psi t opt, because it's a squeezing at the optimal time, which scales as 1 over n to the power 1/3. So the larger the number of atoms, the larger the gain. So here we have a huge gain, but we also, in our paper, have taken a much smaller sample, not to scare too much the experimentalist, and it works also very well. Now, I show you another example. Basically the same thing. The difference is here that in the third image, so for the first image is still the original signal. The second image is what we get for independent atoms. And now the third image is what we get with a squeeze state, but that is not perfect. That was obtained in presence of some decoherence. In particular, we were obtaining the squeeze state in presence of some dephasing mechanism represented by the master equation here. So you see there are some jump operator proportional to SZ. This is some collective dephasing. In that case, the gain that one, quantum gain that one obtains is smaller, scaling differently, scaling less favorably with n, but it is still far enough to recover very well the image. And finally, the other thing that we were showing is that it is actually not necessary to measure all the Hadamard coefficients. One can do a compressed sensing. That is, one can only measure the first Hadamard coefficients, and put the others to 0, and then reconstruct the image anyway. And so this is what is shown in this figure. The first one is the signal as usual. And then in the second picture here, this is for independent atoms. Instead of measuring 512 square Hadamard coefficients, we measure only 64 square, so much less. And we recover something noisy. And if we do the same thing with the same number of measurements with the squeeze state, the image is much nicer. Is this image top right? Measuring 64 square Hadamard coefficients. And then in the bottom right figure is the same thing, but with a non-perfect, non-ideal squeeze state obtained in presence of some decoherence. Okay, so to conclude, I was telling you that one can use quantum correlations among the atoms, spin squeezing, to reduce the statistical noise in parameter estimation when using atomic sensors. And this is, for example, in clocks, but for us here is multi-parameter estimation. I was telling you that one can create these correlations, spin squeezing, using atomic interaction in two-component Bose-Einstein condensates, and even that one can freeze these correlations in an optical, when the atoms are distributed in an optical lattice. And this is a little bit different kind of entanglement, because it's distributed into spatially separated mode that are accessible individually. And I was showing you that this system can allow for multi-parameter estimation, for example, for sensing an extended field with quantum gain. And I was showing you some picture for an image, 2D image. And also, I told you that one can perform some compressed sensing, that is, perform less measurement than the one that would be needed if I would locally measure all the fields. And then I did not tell you, but you will find these informations, further information in the paper if you're interested, that we were not only exploring the possibility to use squeeze state, but also over squeeze state that give a larger gain. And we were showing that it is also possible to measure a vector field, that is something that is unknown, not only the modulus, but also the direction. And the paper is here, open access, published in SciPost, and I thank you very much for your attention.
Thank you, Alicia.
So if you have questions, don't hesitate.
I have one question, Alicia. May I, Chairman?
Yeah, please. Go ahead, please.
Alicia, what is the underlying Hamiltonian you used in your study? A 2D Bose-Hubbard or something else?
So there are two parts. That is to show that you get the spin squeeze state there. That is for this part, we are just for the part of multi-parameter estimation here. We just imagine that we have spin squeezing by the SZ square Hamiltonian. So here, just internal states. While in the previous work, where we were showing that you can freeze the squeeze states in the lattice here, this is Bose-Hubbard, two internal states.
Okay, thank you.
More questions? Well, I have one. At some point you said, oh, I'm not going to do very large numbers of N because I don't want experimentalists to be afraid of this. But when you have that, when you allow that decoherence, that dephasing, that you have a master equation, the time scale of this process, is it something comparable to what they can do in experiments? How is the situation?
Sure, that is the kind of squeezing that you create and freeze in the lattice occurs on similar time scales as they did it for BEC. So what we were showing is that when you raise the lattice, the time required by adiabaticity, that is, you want to be adiabatic to do this, is already okay. I mean, the time you need to squeeze in condensates is such that you will be already adiabatic. So it's the same kind of time scales. So we know that some degree of squeezing, for example, 10 dB of squeezing can be achieved in this way. And also what you know, of course, was already done is this mode transition. But what was not done is to do at the same time. That is, we want to do at the same time the spin squeezing dynamics and the mode. But it should occur sort of automatically.
Okay, thank you. We still have time for more questions.
Maybe I will ask something.
Yeah, please, Don.
If you have two modes, then extreme squeezing would be twin Fox state. If you have more than two modes, N modes, is there some analogy that can be taken?
Actually, I don't know. I'm not sure that I will answer completely your question. But so here you can take, so you have your evolution given by the SD square Hamiltonian. You can push it, if you push it further in time, you get more and more entangled state. And the most entangled is a cat state, actually. Is a state that is a phase state with two opposite phases that can be turned into a noon state. And so if you freeze, and you can choose which one to freeze in your lattice. It depends on how slowly you ramp. So what we were showing is that you can create you can freeze a GHZ, yes, here in this paper. You can freeze a GHZ state. That is, it would be a superposition where all the atoms are in a mode. They are all pointing some direction, the internal state, plus all pointing another direction.
Yes, in a sense, you answered the other extreme, because in the literature there is discussion both of interferometry of noon states and both interferometry with twin Fox states. These are two extremes, and it depends on the sign of the interaction whether you get this or that. So
actually, with this Hamiltonian, you would get squeezed, then over squeezed, then cats. It is a multi-head cat or Schrödinger cat. This is the kind
so it is like attractive interaction that you are using, apparently.
I don't know what I think.
Okay, we can in the future discuss
anyway, it can be done analytically, solving this.
Yeah, I understand. Yeah. Thank you.
You're welcome.
All right, so let's thank Alice again for the talk.
Thank you. Voilà.
And our next speaker is Luca Salasnich. Luca.
Hi.
Hi.
Maybe I can try to share.
Yes, please.
Okay. Do you see?
Yes, and we see your pointer. Perfect.
Okay.
If you like, I can let you know when you have 5 minutes left.
Okay. Yes. Yes. Sure. Thank you.
All right. All right.
Okay.
The floor is yours. Thank you.
Okay. Thank you. This work has been done in collaboration with Koichiro Furutani, that is a PhD student here in Padova, and Andrea Perali, that is a professor at the University of Camerino. Okay, this is the summary. First, I will discuss the model that we are using to describe a mixture of two-dimensional Bose-Bose gas, taking into account the Rabi coupling between the one confined states. Then I will discuss the elementary excitations one can deduce from the model, and also the superfluid density, which is obtained at finite temperature using the Landau formula. And then I will discuss how to get the renormalized superfluid density, taking into account the presence of quantized vortices. And from it, we will also calculate the Berezinski-Kosterlitz-Kataulitz critical temperature, showing a phase diagram for this system. And finally, I will discuss also the behavior of first and second sound modes in the system. And finally, some conclusions. So we are considering a two-dimensional bosonic gas that is confined in a quadratic region of area L, quadratic area L with the size L, so the area is L squared. And the bosonic gas is characterized by two hyperfine components with the bosonic field psi1 and psi2. The Lagrangian density of the system is the one shown in equation 1, where you recognize the familiar evolution term, the kinetic term, the interaction G. Actually, G is the intraspecies interaction. I am assuming that this contact interaction for component 1 is the same of component 2, so G11 is equal to G22 and equal to G. But there is also the interspecies interaction, G12, which is instead assumed to be in general different. And in the second row, you see that there is also the familiar Rabi term with this omega R, that is the Rabi frequency. Which clearly drives the exchange of atoms between the two components. And indeed, the presence of Rabi coupling implies that only the total number of atoms is concerned, while the number of atoms in the hyperfine 1 and hyperfine 2 generally are time dependent. Obviously, if you are considering time-dependent problem. The existence and stability of a symmetric ground state where you have the same number of atoms in the two components, and this has been previously studied in the papers of Abad and Recati, for instance, and also another one. And in addition, the symmetric configuration, in addition to the symmetric configuration, the ground state has also the possible non-zero population balance, but with different values of interaction parameter, and we will not discuss this case, however. Here we focus on the symmetric and uniform configuration, analyzing some effects both at 0 and also and mainly, let's say, at finite temperature. So at the mean field level, at 0 temperature, the symmetric and uniform ground state is characterized by having the same number of particles in the two states, and I denoted with small n1 and small n2 the number densities, which is equal to the total number density small n divided by 2. And the chemical potential of the system, mu, is related to the density small n with the equation 4. And in this equation, you will see that it appears G, that is the intraspecies interaction, but also this eta, and eta actually is simply the ratio between the interspecies G12 divided G. And clearly it also depends on the Rabi coupling, which is, however, a constant in the chemical potential. And it's possible to prove that this symmetric and uniform ground state is stable under the conditions that are shown in equation 5, and or if you want in equation 6. This was this part was done by Abad and Recati some years ago. So there are some conditions that must be satisfied such a way that your uniform and symmetric system is stable. And stable with respect to what? Well, stable with respect to excitations. And it's possible using the Bogolyubov machinery to deduce the Bogolyubov spectrum of the elementary excitation above this uniform system. And actually, one finds that the elementary excitation has two branches that are here are denoted with equation 7 and equation 8. And in particular with minus and the plus. And one of the branch is gapless, that is equation 7, and the other one, the one with the plus, instead is gapped. And in particular, in the gapped equation appears two parameters, capital A and capital B. And these two parameters can be expressed in terms of the chemical potential and the strength of the interaction and the Rabi coupling and Rabi frequency, sorry, as shown in equation 9 and 10. So repeat, there are two branches, one is gapless and one is gapped. And if you consider, say, small wave numbers, so small k, the elementary excitation are a bit simplified, as shown in equation 11 and 12. And you recognize in equation 11 the typical phonon spectrum with that is linear in the wave wave number k, and the speed, let's say the Bogolyubov speed of this phonon, speed of sound of this phononic spectrum is given by equation 13, and as you see, depends on the strength of the interactions and also the density of the system. But there is also the other branch, which is gapped due to this square root of b, and then it proceeds quadratically instead. Okay. Now, what is truly remarkable is that simply knowing the spectrum of elementary excitations, one can deduce the superfluid density of the system using the familiar formula of Landau. And the formula is here. So the idea is that the superfluid density at finite temperature, that is here denoted with capital T, is nothing else than the total density that is, in this case, somehow fixed and temperature independent, minus the normal density, which depends on the temperature. And the normal density has two components, and the two components of the normal density are exactly related to the two components of the two branches of the elementary excitation. So I have this n subindex n with the superindex minus and n subindex n with superindex plus for the two corresponding to the two branches. And the formulas are equation 15 and 16, and they are simply a generalization of the familiar formulas of Landau for the elementary, for the normal density. And what is important is that in the formulas 15 and 16 and 15 and 16, it appears the derivative of this F sub index T. And this F sub index T is nothing else than the Bose-Einstein distribution for the energy, capital E. And so calculated at the corresponding branch of the elementary excitation. So knowing the branch of the elementary excitation from these formulas, you can get the superfluid density. And explicitly, if you do the calculation, for instance, at low momenta, you get a nice formulas for the two contribution to the normal density that are equation 16 and 18. And in particular, if you consider the simplest case, eta equal to 1 correspond to having the interspecies coupling equal to intraspecies couplings. In this special case, the superfluid density becomes extremely simple and given by equation 19. Okay, and obviously you see it depends also on the Rabi coupling. Now, this result for the superfluid density, however, does not take into account the possible formation and of quantized vortices at finite temperature, which are truly relevant in two-dimensional systems. As we know, the superfluid density calculated with the Landau formula goes to 0 at a critical temperature, which is unfortunately larger than the critical temperature of the Brzezinski-Kosteles-Cowles phase transition, which takes instead into account the formation of vortex-antivortex space and the unbinding of these pairs. But however, fortunately, it's possible to adopt also in this case the Kosteles-Cowles approach, extending it somehow, and in this way to derive and solve, deriving and solving renormalization group equations. For our case, we can derive a renormalized superfluid density, having as a starting condition the Landau superfluid density. So starting from the Landau superfluid density, inserting the Landau superfluid density as an input in the renormalization group equation of Kosteles-Cowles, at the end of the calculation, you can get the renormalized superfluid density, which has the nice properties of going to 0 at the Brzezinski-Kosteles-Cowles critical temperature. And this is exactly what we did in a recent paper published in Physical UA. And here I am showing the Kosteles-Cowles equations, renormalization group equation 20 here. Notice that in this equation 20, there is this theta function that is a function of omega r, that is the Rabi frequency, and this theta function, as shown in equation 21, is simply 1/2 if omega Rabi is equal to 0, and instead is 1 if omega Rabi is different from 0. This is a quite strange expression, which is, however, confirmed by numerical calculation, Monte Carlo calculation done some years ago by the group of Nitta in a paper published in Physical Review Letters. And what is important to stress is that this 1/2 that appears in the equation takes into account that in the special case of Rabi frequency equal to 0, is also possible, and also actually is the dominant contribution, the peculiar formation of half vortices, which is, however, instead forbidden somehow with the Rabi coupling different from 0. Half vortices actually means that you can create a system you remember that you have a two-component system, and half vortices actually simply means that you have one vortice in one component and zero vortices in the other component. Okay. Instead, if you have omega different from zero, the preferred configuration is the one in which you have one vortices in one component and another vortices in the other component. Okay. Now, taking into account the equation and solving them, one can calculate the renormalized superfluid density that is shown in this plot as a function of the temperature. And here is shown for three different values of the Rabi frequency. For instance, Rabi frequency equal to 0 is the black blue, let's say black blue dots, and instead the green correspond to Rabi frequency 1. Well, 1 obviously in some units. Here, notice that this omega r bar is simply h bar omega r divided some characteristic energy, in such a way that you are working always with adimensional quantities. And an intermediate value is with omega r 0.1 is the yellow, correspond to the yellow points. And in all these cases, you see that you have a sort of a jump of the superfluid density at a critical temperature, and above this critical temperature, the superfluid density is strictly equal to 0. And in this way, you can deduce what is the critical temperature. Well, you can also do a more, let's say, nice plot, a three-dimensional plot, in which you can put in one axis the temperature, in the other the Rabi frequency, and in the third axis the superfluid fraction. What is important to stress is that our renormalization group equations give a modified Nelson-Kosterlitz criterion that is given by equation 22, namely, just above the critical temperature is related to the superfluid density calculated at the critical temperature by equation 22. And also in this case, however, there is this function theta, which is equal to 1/2 if the Rabi frequency is 0, and instead 1 if the Rabi frequency is different from 0. And again, this result is consistent with the recent Monte Carlo calculations. If you want to see the plot of the critical temperature as a function of the Rabi frequency, this is shown here in this plot for three different values of the G tilde, where G tilde is nothing else that the G, namely the intra-species interaction in adimensional units. And however, you notice that here for three values of G tilde, and actually here I wrote maximal critical temperature because it's the maximum value taking into account all the possible values of G12, that is instead the inter-particle interaction strength. And you see that in general, the critical temperature increases by increasing the Rabi frequency. Also, if then actually it reaches a sort of a plateau. This is the most important plot, if you want, that is a sort of a phase diagram in which you have in the horizontal axis eta, and remember that eta is nothing else that the G12 divided by G, namely the inter-particle interaction strength divided by the intra-particle interaction strength G on the horizontal axis, and instead in the vertical axis you have the critical temperature. And for instance, here there are different values of the Rabi frequency. For instance, if you consider Rabi frequency equal to 0, you have this blue line here, where you have the superfluid state below, let's say, this blue line. Above the superfluid, you have the normal configuration, and let's say on the right of the straight line, that the vertical straight line that is plotted here, you have actually the polarized phase. So you have to consider this region here, superfluid and normal. And on the right, you have the polarized phase, and on the left, you have the unstable phase. Now, if you switch on the Rabi frequency, for instance, 0.1, you have the orange result for the critical temperature, and the region is enhanced, and you have a region where you have superfluidity below this dashed orange curve here. And above it, you have the normal configuration. And on the right of the vertical solid orange line, you have the polarized phase. And instead, in the green region, you have the unstable phase. Then, if you further increase the Rabi coupling, you have the green region, let's say, and the green dashed line is the critical temperature, and above it you have the superfluid phase, and below it you have the superfluid phase, and above it you have the normal phase. And again, on the right of the vertical solid line, you have the polarized phase. So you see, changing the Rabi frequency, the phase diagram is changing strongly. Well, just to conclude, I have, I think, 10 minutes, 5 minutes, maybe maybe a bit more. I want to stress that we can use the Landau approach also to calculate other interesting properties, in particular the first and second sum. As you know, Landau was formulating the fluid theory, where in general your system is superfluid system has such that the total density, as shown in equation 24, is the sum of a superfluid component and a normal component, the one that I discussed previously. Now, another important result of Landau is that if you say you are working, say, close to equilibrium, and you're doing a sort of small perturbation around the sort of uniform superfluid, considering, say, small deviation around the equilibrium for the density and also for the temperature. So you are somehow doing a small perturbation of the density and the temperature around the uniform and stationary configuration. After some calculation, linearizing the equation that you will get, that start, let's say, from the two fluid equations of Landau, you will get a nice equation that is equation 25. It's truly a fantastic equation, and it is a quartic equation for C, and C is the speed of sound. And the speed of sound C is obtained solving this quadratic equation that is actually biquadratic. And in this equation appears other velocities that should be put as an input in the equation, that are this VA, VL, and VT. Now, who are VA, VL, and VT? Okay, say VA is the so-called adiabatic velocity, which is somehow related to the partial derivative of the pressure of your uniform and equilibrium system with respect to the density, calculated at fixed entropy and volume. That is equation 26. However, you have also the so-called entropic sound or Landau velocity, which is given by equation 27. That is a much more complicated expression, which depends on the derivative, you see, on the entropy, But this S with the bar actually is the entropy divided the total number of particles, so the entropy per particle. In this formula, however, you see there is also the ratio between the superfluid density and the normal density, and there is a denominator also the partial derivative of the entropy with respect to the temperature calculated at the fixed number of particles and volume. And finally, there is also the, well, this is much simpler, the isothermal sound velocity, which is simply related to the partial derivative of the pressure with respect to the density calculated at fixed temperature and volume. Now, if you have the pressure and the entropy and the superfluid fraction, you can calculate these quantities, and from these quantities, you can calculate the two sounds. Now, you need the pressure and the entropy. Well, to calculate the entropy and the pressure, you can use equation 30 and 31, which give the pressure and the entropy in terms of the Helmholtz free energy, doing some partial derivatives. And for the Helmholtz free energy, you can again use the elementary excitation that I have shown at the beginning. So the Helmholtz free energy in our approach is simply the Helmholtz free energy, say at zero temperature, which is the mean field 1 if you want, plus the contribution, the thermal contribution that is related exactly to the elementary excitation, as shown in equation 29. So doing everything and doing all the calculations, at the end, you can calculate the first and second sound. So that are the two sounds associated to the B-quadratic equation that I have shown previously. Usually the first sound is the highest and the second sound is the lowest of the two. And you will see in the plot, say in the panel A, we have the speed of sound for well, I don't remember what I wrote here. However, for sure there is on the horizontal axis there is the temperature. So they are the speed of sound of the function of the temperature, and you see the pink line is the speed of sound, first sound. For omega equal to 1, and the blue dashed is this again, the first sound for omega instead equal to 0. And correspondingly, there are the green line and the yellow line for the second sound. What is important to say is the second sound is going to 0 at the critical temperature, and above the critical temperature it disappears, while at the critical temperature, the first sound changes strongly. However, also above the critical temperature, it remains finite. And yes, and so now actually, yes, okay. Now, actually, I don't remember the difference between A and B, but the main message is that, okay, the first sound remains finite also above the critical temperature, and the second sound, as you know, goes to 0 above the critical temperature. And moreover, it's important to stress that there is a strong dependence on the Rabi coupling. Okay. To conclude, we have investigated the Berezinski-Kosteles-Taules transition in a Rabi-coupled binary Bose mixture under the condition of balanced densities. We have found that the renormalized superfluid fraction and the BKT critical temperature are strongly dependent on Rabi coupling and interaction strength. We have also studied the first sound and second sound velocity in this binary Bose mixture by adopting and extending the Landau's to fluid model. Thank you very much for your attention.
Thank you, Luca, for this wonderful presentation. We have time for one question.
I have one.
Yes.
Please, Vanderlei.
It's when you show the diagram towards the end of the talk, it seems that you have some quaternary points where different phases will get together, right? The unstable, the superfluid, the
yes.
That's very interesting in those quantum systems, right? And what is the behavior of the system when you go on that neighborhood?
Okay, well, I don't know because I have not done. However, the phase separated means simply that say you have indeed instead of having a mixture, so the atoms, some atoms tend to stay in one part of the volume and the other atoms in the other side, say, of the volume. Instead, the unstable means somehow truly that the uniform configuration is not possible. So there should be some the density will oscillate. So we are considering this is the special case in which you have truly a mixture. So both special species 1 and 2 are mixed, and the density remains uniform. And we were studying the elementary excitation and critical temperature in this regime. However, if you change the interaction strength and the Rabi coupling, you can enter in regimes which are quite different. One regime is, say, phase separation, where you are still, if you want, the density remains uniform, but if you want, the density is uniform for species 1, but then the species 1 has a lower density. So it's not really uniform. So there is a discontinuity in the density of species 1, and similarly for the species 2. But however, there is only discontinuity. But if you are apart from the discontinuity, the density of the two species are still constant. Instead, when the system is unstable, I think that I don't know because I have not done the calculation, but I guess that there truly is possible to have regions where all one species or the other species or the two are uniform. So you should have some kind of oscillation as a ground state.
Thank you.
Or maybe because this regime is the one where G12 is negative, it's also possible that this is the regime where you have a sort of collapse of the system. Yes. But I have not studied this in detail, so I cannot tell you. However, you know that the collapse, is strictly speaking, is an artifact of the contact interaction. If you include a finite size interaction, you never have truly a collapse of the system, a quasi collapse, if you want.
So let's thank Luca again for the presentation.
There is another question, maybe from Alice.
I think Alice has a question.
Oh, sorry, I didn't see you.
Yes, excuse me, just a short.
Yes.
If you could comment a little bit more, so you find these two branches of excitation, it's very important for the whole thing. So can you describe us what are exactly? I know the case without Rabi coupling, and you have two
without Rabi coupling, they are gapless both.
Because
so
then physically there is the one in which the two species go together, so you have usual sound waves, and the one in which you have a fluctuation in the density difference. That is, you have sort of going towards a separation. And so, but now you have these two different branches in the presence of the Rabi coupling.
Yes.
So is there a simple picture of what do they represent, the one and the other, the gapped and the gapless?
Well, I don't have a simple picture in mind, I must admit. Also because, as you have seen, clearly you can associate to the gapless branch a sound, the Bogoliubov sound. You cannot do it for the gapped one. And if you calculate the first sound and second sound of Landau, let's say, they are strongly dependent on the Rabi coupling, and they are there also if the Rabi coupling is zero, clearly. And so I must say that I don't see a simple picture which relates the presence of the gapped branch to some sound. But maybe there is.
Gapped
but
only in presence of Rabi coupling, I guess, is gapped. Otherwise,
yes. If you see the formulas, you will see that if omega r is zero,
then it's not gapped.
Yes, exactly. Yes, it's truly dependent on the fact that there is the Rabi coupling, the presence of the gapped branch.
Thank you.
You're welcome.
Okay, now I can see everyone. Nobody has their hands up, so thank you, Luca.
Thanks a lot.
And our next speaker is Andrea Richaud. Andrea.
Hi, good morning, good afternoon, everybody. Can you see me? Can you hear me?
We can see your. Oh, okay. Now we can see your presentation. And can you please move your mouse? Yes, we can see your pointer too. Perfect.
Okay, very good. So good afternoon, everybody. I am Andrea Richaud from UPC, Universitat Politècnica de Catalunya in Barcelona. And first of all, I would like to thank the organizers and especially Vanderlei for giving me the nice opportunity of giving the talk. And the topic of today is ghost vortices and how to turn them real. So first of all, I know that you are super experts of quantum fluids, vortices. I would like to start with an example of a very macroscopic vortex, which is made up of dog puppies that swirl around their bowl. And it's a simple but concrete example of coherence. Indeed, a vortex is a region in a fluid in which the flow revolves around an axis line. And here you can see that the deeper you go towards the vortex axis, the faster your particle revolve. And the idea of a real, let's say, a usual real vortex is the following. You have a wave function. In this case, it's a wave function defined in 2 dimensions that is defined by a square modulus and by a phase. And typically, the phase rolls up from 0 to 2 pi, and the density goes to 0 at the vortex center. This is a typical vortex. The ghost vortex is the following. So it's a very particular phase defect where the phase singularity falls in a region where the density is almost 0. This is the definition of ghost vortex. And this is the topic of my talk. Ghost vortices have quite a long history. For example, soon after the first experimental observation of vortices in atomic VEC, the dynamics of vortex lattice formation upon the trap rotation was extensively investigated by means of numerical simulation of 2-dimensional Gross-Pitayevsky equations. And it was in this context that a new class of topological excitation that were termed ghost vortices was pointed out. And indeed, they were described as phase singularities that appeared at the outskirt of the atomic cloud when it was rotated. And then, by gradually approaching the Thomas Fermi boundary from outside, they gave place to surface waves, which ultimately resulted into a dynamical instability. And when this happened, the phase singularities entered the atomic cloud, formed a lattice, and started to give a non-vanishing contribution to the total angular momentum of the system. So, as I was saying, ghost vortices appear at the periphery, enter the surface as a result of unstable surface modes, and migrate toward the bulk to form a lattice. This was the first description of ghost vortices. And here it's the comparison between the density field and the phase field of the same system at different times. So black dots corresponds to phase defects. Another platform where ghost vortices were described is the following. You take a superfluid described by a wave function, you shine a repulsive laser beam, And so you create a density depletion. You create a little spot where your superfluid density goes to 0. Okay, well, then you start translating the laser beam. And we all know that if the translation velocity is high enough, then you create excitation in the form of vortex-antivortex pairs. So the laser beam is seeding the vortex-antivortex pairs. But what I didn't know until some months ago is that the seed of these vortices are ghost vortices localized inside the laser beam. So when you translate the laser beam, you start creating a vortex-antivortex pair that turns into a vortex-antivortex, that turns into real vortex and antivortex. So this is another platform where they were observed. Another interesting platform is a train of quasi-one-dimensional solitons which undergo snake instability until they break up into a chain of ghost vortices with the circulation of alternating signs. And this is the prelude of the so-called vortex turbulence. This is a more recent result done in the group of Nazarenko. Okay. This is, let's say, a brief overview of platforms where ghost vortices were described. This is the platform where which we focused on to carry on our study. So it's a quasi-two-dimensional, two-component BC, such that Psi-A, which is the majority component, features a necklace of real vortices, and Psi-B is localized at the vortex cores. So indeed, we are talking about two different wave functions. Psi-A is the majority component and is a vortex necklace, and Psi-B is just an array of quasi-Gaussian peaks. And the peculiar thing of this system is that since all the vortices in the majority component have the same sign, all the system is rotating around its axis. So let's say the ground state of this system is characterized by a uniform circular motion. And as a consequence, also the core filling component, Psi-B, must rotate together with the hosting vortices. So the two motions should be synchronized. And the only way for these orange peaks to rotate is to have ghost vortices. So ghost vortices are really necessary to support the overall dynamics of the system. To approach the theoretical study of this system, we considered the simplest possible model, theoretical framework, which is represented by two Grosspitajeschi equations coupled by a density-density interaction term. So here we have that the two fluids, Psi-A and Psi-B, interact by means of this density-density interaction, which is assumed to be such that the immiscibility condition is satisfied. So this inequality ensures you that component B atoms stay localized within the vortex cores. And also for the sake of simplicity, we assume that V trap is a circular hardwall trap of radius r. And this can be nowadays, this can be obtained by means of digital micromirror devices. So we have an hardwall circular container, and we are in the immiscible regime. And also for the sake of for convenience, we use the hydrodynamic notation. So we define rho A and theta A as the density field and the phase field associated to Psi-A, and the same, of course, for Psi-B. So what we did was to start solving these coupled Grosspitajeschi equations in a suitable rotating frame. And what we found were configurations of this kind. The first row corresponds to Psi-A square modulus. The second row corresponds to the phase of Psi-A. The third row corresponds to the density associated to psi b, and the fourth row to the phase associated to psi b. And what we see is that psi A is characterized in general by n vortices. In this case, we have just two vortices, so two density depletions that come with a phase defect here. And here we have a black star that stands for the presence of a real vortex. More interestingly, in psi B, we see that we have two localized cores here and here, but we also have two extra, let's say, unexpected phase defects here and here, which are the ghost vortices. And this happens not only for n equal to 2, but also for n equal to 3, 4, 5, and so on. So quite generally, we observe the formation of vortex polygons whose cores are filled by component B atoms, and we always see a sort of, a necklace of ghost vortices, which constitutes a sort of dual lattice. So here, if we have a real necklace, we get almost automatically a dual necklace of ghost vortices. Okay. To approach the problem from a more quantitative point of view, we resorted to the so-called massive point vortex model, which is a model that I've been working on for 3-4 years now. It's something that I developed together with my former PhD supervisor, Vittorio Penna, two Spanish colleagues, Ricardo Mayol and Mounsa Guillemard from University of Barcelona, and especially with Professor Sandy Fetter from Stanford. Basically, this point vortex model allows you to account for superfluid vortex dynamics and inertial physics on equal footing. And you can recognize here an inertial term, which comes from the presence of core mass. And here you can see the standard, let's say, superfluid vortex dynamics. Here, for example, it's the interaction of a vortex with its image. And here it's the interaction of a vortex with all the other vortices and their images. Well, this Lagrangian captures the essential dynamics of the system. You can write the Euler-Lagrange equations, and you can find that there is a notable family of solutions. The notable family of solution is represented by the so-called n-vortex necklaces. So basically, they are regular polygons made up of n vortices. And you get this equation that links the number of vortices constituting the necklace, omega n, which is the precession frequency of the whole system, RR, which is the radius of the circle where the necklace is inscribed in, and mu, which is the ratio between the total mass of the B component and the total mass of the A component. And you can plot this implicit, you can plot this equation by varying omega. You can plot this relation as a function of the radius, and so you can get a relation between the precession frequency omega as a function of RR, the radius of the necklace. And you can do this for 2 vortices, 3 vortices, 4 vortices, etc., and for different values of the core mass. So this gives us the precession frequency of the system as a function of the radius for any mass. Another thing that this point vortex model can output is the energy of the n-vortex necklace. You can compute the total energy of the system. Here it's the result. I skip the details, but you can recognize the kinetic term that comes from the presence of these masses that are orbiting. Here there is a sort of 0-point energy, which is the energy cost to create one vortex. And here it's the energy of the interaction energy between the vortices. And in the same way, you can compute the total angular momentum of the system. And again, you can recognize the classical part here, which is due to the masses that are orbiting, plus this, let's say, quantum term, which is due to the intrinsic contribution. It's the intrinsic angular momentum that the vortices bring to the system. And when you have these formulas, you can plot this, let's say, this very well-known plot. Here it's the angular momentum of the lowest energy configuration as a function of omega. So you can see that there are sets of critical frequency at which it gets energetically more convenient for the system to add one vortex to the system. And we can see that the presence of mass alters this set of critical frequencies. But there is another aspect that, in my opinion, it's quite interesting, is that even in the presence of mass, we have the so-called transition from the 5 configuration to the 5+1 configuration. So it means that when we have a pentagon of vortices, and if we increase the rotation further, it's energetically more convenient for the system to add one extra vortex at the center rather than to form the hexagon. This is a quite old result that was originally observed in superfluid liquid helium in 1979, and that was later explained and discussed in the work by Kim and Fetter. Okay, but I don't want to spend additional. I don't want to focus on the prediction of the massive point vortex model. I just want to mention that it is useful to do a lot of interesting physics. For example, recently we studied the dynamics of massive superfluid vortices in air-to decay confining potential, and we saw that the mass is responsible for the inversion of the precession. So the precession of a vortex can be reversed due to the presence of core mass. Here with the Trento group, we studied the possibility to have 2 vortex collisions, so the annihilation of vortex-antivortex pairs, and also the stabilization of vortices with charge greater than 1. And this one is also very recent. With the Trieste group, we studied the dynamics of superfluid massive vortices in annular geometry. And this will be the topic that my colleague Matteo Caldara will discuss tomorrow at 4:30. So I think it will be very interesting, and don't miss it. As I was saying, today I don't want to discuss further about the dynamics of the overall system, but I want to focus on the properties of psi-b, so the properties of the minority component. As I was saying, the minority component is characterized by a necklace of ghost vortices, which are necessarily present in the wave function of, which are necessarily present to support the overall rotation of the system. And for example, in this simulation, I can tell you that the density here, at the position of the ghost vortex, it's 1,000 times smaller than the peak density. So this is the peak density. The density here is 1,000 times smaller, but they are crucial because they induce a non-zero phase gradient in regions where the density is high. So here you have a phase defect here, but this phase defect induces a non-zero phase gradient here where the density is high. And that's why, let's say, the ghost vortices are really necessary. And yeah, they arise because psi-b must be continuous and single-valued, and because the velocity field associated to the minority component must be irrotational. Also, another interesting observation is that let's imagine to do the following TOF experiment. Let's imagine to have just 2 massive vortices, and let's imagine to glue a compass with a tiny arrow on top. And let's wait for the system to perform a rotation of pi over 4. We have 2 possibilities essentially. Either we get this result or we get this result. The lower one, panel C, is wrong because this is what would happen if the cores were rigid bodies. And this is not the case. The cores are superfluid, so they do not rotate. They cannot rotate as rigid bodies. And in a sense, they precess, but keeping their orientation constant. They cannot rotate around their own axis. This is the meaning of this picture. And indeed, this circumstance is compatible with the presence of two ghost vortices here in the perpendicular direction. Well, is it possible to estimate the number and the position of ghost vortices? The answer is yes. We can estimate the position of ghost vortices simply by requiring that the azimuthal velocity characterizing the uniform precession of a massive vortex in an N necklace exactly matches the velocity vector field evaluated at position RR. So we know from our massive point vortex model the precession velocity. We just need to require that it is equal to the velocity field associated to the phase, the velocity field associated to the minority wave function. And with this very simple observation, we can make the following ansatz. Okay, this is an assumption which will turn out to work quite well. So we assume that the phase field of the minority wave function is simply the superposition of n arctan function. So it's the usual fingerprint of a vortex, the arctan function. So with these ansatz, we developed some tedious algebra. We get the following equation, which links three essential quantities: the position of real vortices, RR, the position of ghost vortices, RG, and the precision frequency of the whole system, omega. So, and also what we discover is that the only platform-dependent parameter is the ratio between the atomic masses of the two components. So it's a quite universal equation. And if we plot that equation as for different values of n, so here we have n equal to 2, n equal to 3, 4, 5, for different masses, we obtain the following picture. So we have a very precise relation between the position of real vortices and the position of ghost vortices. Let's imagine to tune the omega, which is the overall precession of the system. By tuning omega, we draw these curves, which are obtained in an analytical fashion. And we find a wide linear windows whose slope does not depend on the core mass, but only on the atomic mass ratio. This is the equation of this linear segment. And so we have found analytically a relation between RG and RR for different masses. And what we did was to compare this analytical prediction with data extracted from Gross-Pitaevsky simulations. So basically, we really measured the radius RR and the radius RG to compare with the analytical prediction, and we indeed had a very nice agreement. Okay, of course, there are degenerate cases. For example, here we can see that we are in a condition such that the radius of the ghost necklace is going to 0. So what it means is that your necklace of ghost vortices is squeezing, and what you get is a single ghost vortex of charge n at the center. On the other extreme, on the right, we have the breakdown of the ghost vortex necklace and the emergence of much more complicated structures. So here we don't have a simple dual necklace of ghost vortices. Here we get 9 ghost vortices. So these are more complex, let's say, patterns of ghost vortices, which I'm not going to discuss further. And for the last part of my talk, I would like to answer a question that some of you may have. So you may argue, okay, these phase defects are very elusive. They may be so fragile that they have basically no way to be observed. And indeed, this is wrong. And as I will show you, these phase defects have a physical importance, and they can be observed by means of a suitable quench protocol. And the quench protocol that I'm now suggesting to observe these ghost vortices is the following. The idea is borrowed from standard fluid dynamics experiments where colored smoke is injected to probe hidden or unknown flow patterns. So here we have an airfoil. You inject green smoke and you see the vortex, the flow lines. In a similar way, what we do is to take our system and quench the interaction parameter GAB. More precisely, we half it. So we reduce the interspecies interaction in such a way that some of these orange atoms are expelled from the necklace, and they start to diffuse around here in this blue sea. And the crucial thing is that this diffusion is not uniform. This diffusion is strongly affected by the underlying presence of ghost vortices. So somehow, while diffusing these orange atoms, they feel the presence of the ghost vortex, and they dress him, giving him a non-zero density background. Let me show a concrete example. So we start at time t equals 0 with our localized cores, and we release part of them by quenching the interspecies interaction. Here, the bosons are starting to diffuse, but the diffusion is not isotropic, it's not uniform. They swirl around what were the original ghost vortex position. So we are dressing the ghost vortex, and eventually we have made them visible. So we started from 3 ghost vortices, and we end up with 3 real vortices. We have dressed the phase singularities, making them real.
Andrea, 5 minutes.
Yes, I'm about to finish. Thank you. This is the complete video of our numerical simulations. As I was mentioning, the GAB is quenched in such a way to be reduced by a factor 2. And yes, we are seeing that the bosons are dressing the ghost vortices and are turning them real. As a last topic, we proposed an indicator to quantify the degree of realness, or the degree of ghostliness, if you want, of a phase defect. And again, the inspiration came from another field. In this case, is computer vision algorithms that are used to perform edge detection. Basically, this is a very difficult sentence, just to say that we computed the local curvature of the density field at the ghost vortex. So take the density field of the minority component, compute the Laplacian, and evaluate in the neighborhood of the phase defect. And this indicator has 2 natural bounds. The lower one is 0. So if you have a poorly ghost vortex, then this is 0. And there is a sort of upper bound, which is of the order of rho 0 divided by psi squared. And that is for a perfectly real vortex. So if you have a typical uniform density plateau with a vortex, the curvature is of the order of rho 0 divided by psi squared. So we applied this indicator to our proposed quench protocol, and we indeed see that the indicator starts from 0. Here we start from a purely ghost vortices, and the indicator is 0. Then along the dynamics, the indicator increases, and here, for example, it is significantly different than 0, and it corresponds to the onset, let's say, to the manifestation of real vortices. With this, I come to the conclusion. I have just 3 take-home messages. We demonstrated the existence of ghost vortices in a superfluid, psi b, which fills the course of real vortices of another superfluid, psi a. we have predicted the functional relation between the position of real vortices and that of ghost vortices, and benchmarked it against Gross-Pitayevsky simulations. So as far as we know, it's the first analytical description of ghost vortices. So the first analytical estimate of the position of these phase defects. And eventually we have proposed a feasible, an experimentally feasible quench protocol to do the direct imaging of these hidden phase defects. And with this, I would like to thank you for your attention, but especially I would like to thank my collaborators, especially Andriy Chaika, who is a brilliant master student from Kyiv University. And he is not only is brilliant, but he is managing to carry on his research in spite of all the difficulties that, of course, there are now in Kyiv. And also I would like to thank Professor Alexander Yakimenko, who is also from Kyiv, but in the meanwhile, he moved to Padova in the group of Luca, I guess. So thank you very much for your attention. I list here a list of references concerning the dynamics of vortices with field massive cores, in case you are interested. And of course, I'm open to questions. Thank you.
Thank you, Andrea. Do you have any questions?
I have one, Lucas.
Go ahead, Vanderlei. Yeah.
The question is, when you have the, well, it was a nice talk.
Thank you.
But when you have the massive, how is the interaction between the vortices? Because normally when we deduce the interaction, like the, you know, the charge interaction, like
yes.
current interaction,
yes.
we use, you know, equivalent to electromagnetism
yeah.
and things. But here, how are you going? How we need to change the?
It's a very little. It's a very little change. The only extra term is this one, the inertial term. All the other remains unchanged. So the Coulomb line.
But then, you know, I cannot really deduce the interaction, like, you know, the force as being the force between like electromagnetic current, because now I have a.
No. Actually, I have some backup slides I'm happy to share. Indeed, we proved this model in a rather rigorous way, thanks to Sandy Fetter, who had the idea to apply the time-dependent variational Lagrangian, which is, let's say, a rigorous way to approach the problem. So,
I believe that. So the answer is no. The very little change because of carrying that mass. And of course, the second question is when you have a massive vortices, and if we want to consider reconnection and things like this, annihilation of vortices, anti-vortices, how that comes? I mean, what's happened with that mass that you have in there?
Well, for example, I can show you, how can I share the screen again? Just a second. I cannot share the screen anymore.
That's okay.
The screen, but
I wanted to show an example of two vortex collisions.
Oh, okay.
How can I share the screen?
You are sharing the screen, but we see your wallpaper.
Okay. So let me do it full screen. Okay. So here we have two vortices and two massive cores. I want to show you the video of the annihilation. This is a vortex-anti-vortex pair.
Massive, right?
Massive, right? Here you see the presence of. It doesn't. Sorry. The video doesn't work on this format. Usually, okay, we have this kind of situation. So the vortices touch, and you generate an explosion of sound waves. So the incompressible kinetic energy, which was due to the vortices. Can you hear me? Yeah. The incompressible kinetic energy is converted into a very big sound pulse, and but still the mass remains here in this little blue dot. This is the leftover of the core mass. So this is not a vortex. This is just, let's say, like a drop of oil in a soup. This is just due to the...
It's an impurity in the soup.
It's an impurity. It's an impurity.
Okay. Andrea, can you send me... I took some notes of your references, but if you can send me the link for some of your movies, I appreciate it. I will understand that.
Of course.
Okay, thank you. Just before, Luca, we have to say that tomorrow we return at the same time, right? We will be 12 o'clock in the UTC time. And we have a very nice collection of talks for tomorrow. So we appreciate it to have everybody present as we had today. Thank you very much.
And I think Ophir alone.
Yes, I have a question.
Yeah.
Thank you.
Oh, sorry, Ophir.
It's okay.
Yes.
It's late. Andrea, I have a question. Maybe you can suspect. Your study is mean field, yes? Fully
yes, fully mean field.
What do you think will happen to the ghost vortices at the many-body level? I mean, there are two effects. One is depletion, and the other one is entanglement between the two, the two components. So,
yes,
what will happen?
It's a very good question, and I fear I don't have an answer because I never worked on that. Indeed, here in Barcelona, we are there is a strong group of Quantum Monte Carlo with Jordi Bogonat, Grigori Strakacic, and we are considering extending our studies beyond the mean field, but we have no results yet, so it's difficult to anticipate an answer.
Okay.
But it is indeed a very nice.
There is a paper published several years ago about phantom vortices. I mean, when you get depletion, what's going on to the angular momentum acquisition in excited modes. I think if you look at the term phantom vortices, you will find the paper. I think it's a scientific report, not mine. And you will find some clues what might happen.
I think I included, now that you tell me, I remember it, although I didn't read through it, because I included it in the introduction, but the term is not new. I will read it more carefully.
Okay.
Thank you.
I think I saw Doron Coin raise his hand, or no? No? Yes? Okay. Yes, please go ahead.
We cannot hear you. We cannot hear you.
You're muted.
Sorry, before I raised my hand because I thought that it ended, but then Ophir said that he has a question.
So, do we have any more questions? No? Let's thank Andrea again.
Thank you to you. Thank you very much.
And, well, Vanderlei just asked me to remind you that tomorrow we start at the same time, 12 o'clock UTC. Any more comments, Vanderlei? No? All right, so see you tomorrow.
Bye. Bye-bye.
Bye-bye.